Alright, this is my first reassessment for chapter 14. Uh, I pretty much got well, I found a problem in a book, and pretty much one of the hardest problems that I noticed in the chapter, and created my own problem similar to it. So, kind of what you got going on here is three different points of interest. You got a dipole here, you have a sphere here, and then also you're going to have location A, which according to these coordinates here, these vectors, location A would happen to be probably somewhere around where I wrote location A. As weird as that is. Um, so we have charges on the dipole of 2 nanocoulombs, and let's see, they are also a distance of 1 millimeter apart, which would be S in my formulas. And then over here on the sphere we have big Q would be negative zero point 0.3, and the radius of the ball, which I don't think matters, is 3 centimeters. Ignore that vector there. It was just from whenever I was working the problems, I was using that for myself. Okay, down here, so the question is, what is the net electric field at location A? So the net electric field is going to be the sum of the electric field due to this dipole, and then also the electric field due to the sphere. So you're going to have to add those together, and that gives you the net electric field. So the first thing we want to do is find the electric field of either the dipole or the ball. So I think here I did the dipole first. It's kind of hard to see. I know it's tiny, so you're going to have to bear with me. Okay, so first I found the distance between the dipole and the location A. So that'll give you what's going to be known later as being R. So, man, it's already been 2 minutes. I'm going to have to keep this under 5 minutes. So I'll try to fly through this. Anything interesting going on here? Not really. I'm just filling it in. It is kind of weird that I got such a small number, 0.288. I thought it was weird. I worked it out like a million times, put it in the calculator over and over again. I kept getting the same thing. So I hope there's nothing wrong there. Yeah, since only the y component changes. Let's see. Yeah, since only the y component changes, I'm only left with one value for the actual r. So when I plug it in there, yeah, it all looks fine. So then I move on, and gonna start finding the electric field of the ball on location A. So now we pretty much have an entire vector we're doing here. So this part was a little bit more time consuming for me because you're dealing with magnitude of r and r hat and all that stuff, which is pretty much last semester 221. Let's see, anything else interesting that I need to point out? Okay, right here, it's really hard to see. You have the magnitude of r squared, I believe. So when you square a square root, because my magnitude came out to be a square root, when you square a square root, it just goes away. So that's why I just have 0.0029. Let's see, I got the vector multiplied at all times, negative 931.03. Let's see. Okay, I see. Negative 931.03 was what I got when I added. When I multiplied this and this together, and then I had to multiply all that times the vector. Okay, and that's what I came out with. And then down here, pretty much all I did was add the electric field of the ball to the electric field of the dipole and got this vector right here. It it does seem to make sense to me because if you notice here, the electric field of the dipole, this vector, if the location of location A is right around here, that vector is going to be pointing straight up. And then this one over here is going to be more kind of at an angle. So then when you add them both together, it seems to fall, the vector seems to fall right in between those two vectors.